Welcome to Learning Unit 5A, Mechanical Properties of Materials. In this unit we are going to understand how to measure and interpret certain properties, mechanical properties of materials. Understanding these properties is very useful for anybody who wants to choose a material for a particular engineering application. The properties are measured using precisely defined standards, and in the USA, the ASTM international standards are widely used. You're encouraged to look at their website and join their membership. Membership for students is free. When we are beginning the process of choosing a material for a particular application, particularly for a structural application, we want to know what the strength and the rigidity of the material will be under different types of load. For instance, it could be a tensile or stretching load, a compressive or load that tends to squash the material, or torsional, a twisting load. We also want to know what the time period for the application of the force is, whether it would be a very short time or whether it will be a constant dead load. We want to be aware of if there are any fluctuations in the load, particularly cyclic fluctuations, as this will reduce the load-bearing capacity if we have to consider factors such as fatigue. And of course we have to consider the effect of temperature and other environmental factors on the mechanical properties of the material. The design properties that we will introduce in this chapter will relate to the stiffness of the material, its strength, its hardness, ductility, and toughness. First, let us look at the concepts of stress and strain in material science. There are four types of stress and strain that we are going to look at: normal stress, shear stress, normal strain, and shear strain. In order to understand what shear stress and normal stress is, we should understand that those stresses are an example of an internal force in a member. To understand what an internal force is, let's have a look at the member shown in blue. It is under the action of equal and opposite forces at its ends. It is thus in static equilibrium. Every part of this object is in static equilibrium. Now we must think, what is keeping the upper part of the tie in equilibrium? Imagine if we were to make a cut here. What forces need to be applied at the bottom of the cut in order to keep it in equilibrium? We realize that the upper part of the tie must be experiencing an internal force that balances the force applied to the other end in order to keep it in static equilibrium in the original configuration. This internal force acts over an area, and the internal force may be either tensile in nature, which means it is stretching, or compressive. Let's have a look at the internal force. In this case, we see an internal force that is acting perpendicular to the cut cross-sectional area of the member. We know that the addition of all the forces acting on the top area here must equal the force being applied. And that's what this integral says. Except we must understand that sigma, which is known as a normal stress, is equal to the normal force on the cross-sectional area of a member, and that this force is acting perpendicular to that surface. If we divide by the surface area, we normalize for that surface area. In such case we get stress. So stress is the force, the normal force, acting on an area divided by that area. A positive normal force is tension, and a negative normal stress denotes compression. Let's look at shear forces. So let me go to this slide here, where imagine we had both these two forces here, a lateral force and an axial force acting on the member. And if we look at the cut section here, we see that the internal forces are creating a force that is both parallel to the cut cross-sectional area and normal to it. The normal force is shown in red, and the force parallel to the surface, the cut surface, is shown in green. This green force is known as a shear force, and the red force is known as a tensile force. If we divide these forces by the cross-sectional area, we convert them into stress. That's shown in this diagram here. Imagine we have a force acting in a particular direction on an area. If we divide the component of that force that is parallel to the area by that area, we get the shear stress, called here the tangential stress. So those are equivalent terms, tangential stress and shear stress. The component of this force that is normal to the cross-sectional area divided by the size of the grey shaded area is equal to the normal stress. If we were to consider an arbitrary shape and cut a cube inside that volume, so let me draw the rest of the material. So imagine we had some arbitrary object, and inside we took a cube element as shown. On each of the faces of that cube element, on all 6 faces, we can have a combination of shear and normal stress. For this cube to be in equilibrium, we realize that the normal stress on opposing faces must be the same. Hence, that's why this sigma x is equal to this sigma x here. We can do that for all of the faces. I won't go into too much detail here, but the point of showing this is to say that in 3 dimensions we can see that the state of stress of material consists of shear forces and normal forces. But before we talk any further, let's do some concrete examples to explain the idea. So imagine if I have a bar here which is 0.5 inches in diameter. That's 0.5. And if I apply a force of 1,000 pounds to it, what is the stress generated? The stress in this case will be the force P, which is 1,000, divided by the cross-sectional area, which is pi, 0.25 inches squared. And this answer is equal to, just calculating it now, 1,000 divided by pi times 0.25 squared, which is equal to 5,090 pounds per square inch. This is also referred to as 5.1 thousand pounds per square inch is known as a kilo or a KSI. So here we've calculated the stress from the force or the load. So this is the load being applied, and the load causes a stress, and this is the stress. Let's look at an example of shear. Let's say I have a material like so, and let's put this as 0.1 of an inch, and this side is also 0.1 of an inch. And let's apply a force within the plane of the shaded area of 1,000 pounds. The shear stress in this case will equal the force 1000 divided by the cross-section area, which is 0.1 squared, which should equal 10,000 psi. No, sorry, 100,000, of course. Or in other words, 100 ksi of shear stress. Just to give you another concrete example, imagine we are screwing together two plates using a bolt. This is my bolt. Here is one plate, and here is another. And there's a bolt on the other side. I should have drawn the thread. Okay, so this bolt is bolting together these two plates. Imagine I apply a force to this plate, force F, and apply another force to this plate, force of equal and opposite force F. We can see that these two plates want to slide apart, but they are prevented from doing so by the bolt. If we applied enough force, what would happen? The bolt would shear. So let's sketch what that would look like. This would be the top of the bolt, and then the bottom would become displaced. This is the idea of shearing. So it would fail here through this shearing action. The shear stress generated on this hatch surface that I'm hatching in right now is going to equal that lateral force divided by the cross-sectional area of the bolt. Now let's look at the concept. We understand now that the concept of stress is force divided by area. But what is strain? Strain is a measure of the amount of deformation that occurs in a material due to the application of stress. In the case of normal strain, where the change in length is along the direction of the applied force, the normal strain, given by the symbol epsilon, is equal to the change in length divided by the original length, and the change in length is the change in length that occurs as we apply a force to a material. So all materials stretch by a very small and often imperceptible amount, but sometimes it is perceptible. Obviously with a rubber band you can see it quite clearly. In the case of shear forces or shear stress, what happens is that the object under a shear stress will deform like so. So if you imagine taking a book and applying a force to the top surface like so, and to the bottom surface towards the left, you will see that the edge of the book will now have an angle. That angle that it makes with the vertical, if it's small, is the same as the shear strain if that's measured in if that angle is measured in radians. See, what will happen is if we apply a force to this material, it will start to lean over, and the top edge will have moved over by distance x, as shown. Just going to change the color of this. So if we divide that distance x by this distance L, we basically calculate this angle here in radians. So this is x and that's L. So the shear strain, sorry, the title is not visible. Let me write that in. The shear strain is going to equal this distance x divided by the distance L. How do we measure stress and strain simultaneously? This is typically done using a tensile testing machine. In this tensile testing machine, the sample is put between two substantial jaws, and then the top jaw is moved at a constant rate, and the force required to move it at a constant rate is measured using a load cell. If we plot the stress versus the strain of the material, we get a characteristic stress-strain curve from which we can measure many important mechanical properties of the material. Initially, the strain in the material will increase linearly with the applied stress. If we were to reduce the stress at this point, the material would go back to its original shape. However, beyond a certain point, called the elastic limit, the material, when the stress is removed, will end up with a permanent strain. The gradient of the first part of the stress-strain curve has a special meaning. It is called the modulus of elasticity, sometimes given the symbol E. If we were to draw a line parallel to the elastic part or the linear part of the stress-strain curve that is offset by an amount that is equal to 0.2%, the point where it intersects the stress-strain curve is known as the offset yield strength. This procedure is used because it's often very difficult to actually tell exactly when we go from a straight line behavior to a curve. And so this systematic technique is used to determine the point at which the material starts to yield. And this is called the yield strength. If we create a stress in the material which exceeds the yield strength, sometimes given the symbol sigma sub y, then the material will be permanently deformed. In most engineering applications, we want to avoid ever getting close to the yield stress of the material, because that will permanently change the structure. We keep increasing the stress. The strain keeps increasing until we reach a maximum point on the graph here. The maximum value of the stress on the stress strain graph is called the tensile strength. The elongation will continue until the material breaks, until it ruptures. We see in this case that the material has elongated by over 10%. And the strain at fracture is called the elongation to failure. Here we have a ductile material that has failed in a gradual way. So it has yielded, stretched, and then finally broke. The gradient of the first part of the graph tells us how stiff the material is. The higher the gradient, the more stress required to produce a unit amount of strain. And hence, the more steeper the first part of the graph, the higher the stiffness of the material. So here from this we can see that the elastic moduli of steel is greater than the elastic moduli of aluminium or aluminum. Let's apply some of this to this problem here. So let's apply some of the concepts we've learned to the problem. Figure 625, or Figure 621, shows the tensile engineering stress-strain behavior for a steel alloy. Notice they use the word engineering. What does that mean? That means that when we determine the stress simply by dividing the applied load by the original cross-sectional area, even though we understand that as we stretch the material will get thinner and hence the cross-sectional area will get smaller. But however, we ignore this and simply calculate the stress as equaling the force being applied over the original cross-sectional area. Let me clean up that sigma. Not a very good sigma. There we go, a little bit better. So, it says, what is the modulus of elasticity? Modulus of elasticity. So we know that E is equal to the gradient of the stress over the strain. Okay? Or is equal to the stress divided by the strain up to the elastic limit. It's very difficult determining where the elastic limit is, and so they're blown up the graph in the inset. Let's choose a point where we know we are in the linear region of the graph. Right here. We can see here that the stress is 300 megapascals. Pascal is 1 Newton per meter. And the strain at this point is 0.0015. If we calculate that out, we get the modulus of elasticity. Which is, we get an answer, I get an answer of 200 times 10 to the 9 pascals. This is equal to 200 gigapascals. Just make that a bit clearer. Gigapascals. So that's our modulus of elasticity, or Young's modulus of the material. It's asking here, what is the proportional limit? The proportional limit here is quite hard to find because we need to figure out exactly where the graph bends. The inset is helpful here. We cannot be too precise about it, so I will say that the proportional limit is roughly equal to up to 300 megapascals. Now the next part, it says, what is the yield strength at a strain offset of 0.002, the 2% offset yield strength? So let's draw a straight line that goes through 0.002 and is parallel to the linear part of the stress strain graph. So I've drawn that line right there. And now I see where that line intersects the stress strain graph, and it does it right here, and we can see that that occurs at 400 megapascals. So we can see that the 0.2% offset yield strength is equal to 400 megapascals. Corresponds to this point right there. It's now asking, what is the tensile strength? The definition of tensile strength is the stress, the maximum stress on the engineering stress strain curve, and we can see that occurs somewhere around here. I will say it's approximately 500 megapascals. Oops, sorry, that's right here. So here we have calculated 4 mechanical properties. So we have 3 important mechanical properties here. we have the modulus of elasticity, which is a very important material property. We have the yield strength, and we have the tensile strength. This graph shows how the elastic modulus of a material, shown here in giganewtons or gigapascals, on the left and on the right in kilo pounds per square inch, or KSI. We see that polymers have low stiffness. Then we have composites, natural composites here shown, wood grain, and here we have carbon fiber reinforced polymers or plastics, and which have pretty high stiffness. And then the highest stiffness here in the composites area is for cements. We see metals are definitely high up in terms of the stiffness, but the stiffest materials are ceramics, and diamond topping the list as the stiffest material, the material with the highest elastic modulus. When a material is pulled in one direction, it will experience a reduction in size in a lateral direction. So imagine the object started out with the green shape, and then when it was pulled, it is now a prismatic object, but with the cross section shown here in red. So not only has it got longer, but it reduced in width as well. And the ratio between the lateral strain, the strain perpendicular to the direction of the force being applied, and the axial strain is called the Poisson's ratio. The shear modulus is very similar to the elastic modulus. It is equal to the shear stress divided by the shear strain. And to indicate that when we apply an axial stress to a material, we don't just generate normal stresses. We create what is called a state of stress, in which there exists a different ranges of shear stress and normal stress in different directions in the material. And this is shown by the fact that the shear stress, the shear modulus, the elastic modulus, are related to Poisson's ratio by this equation, showing that shear stress or shear strain and normal strain are related. By looking at the shape of the stress-strain curve, we can classify materials according to the level of ductility. The green line here shows that the material breaks before it stretches at all. Such a material is called a brittle material and does not deform much upon loading and eventually breaking. That's why if we have a ceramic vase and we break it, it doesn't deform while it breaks. We can glue it back into its original shape. However, if we had an aluminum object and we bent it back and forth or stretched till it broke, simply gluing it back together would not get us the same shape because it deforms. A material with moderate ductility will have some deformation before it ruptures, and a material with a high ductility will will have a high, what's the word I'm looking for? The word I'm looking for is right here. Will have a high elongation to failure. So we can classify materials as being brittle or ductile according to their plastic deformation behavior. Plastic deformation, that means a permanent deformation that the material of shape due to the application of a force. Here we see an example of a piece of aluminum that has been stretched, and we get a classic cup and cone fracture. And the material tends to form a neck, and at the center of that neck you get tiny voids forming. The voids coalesce to cause a fracture. In a brittle fracture we do not see necking, and the material undergoes very small amount of deformation. Ductility is quantified according to this formula. The elongation at formula, the elongation, percentage elongation, it doesn't have to be at failure, but just if you stretch something and we want to calculate the percentage elongation, we simply take the final length minus the initial length divided by the original length and multiply that by 100 to get percentage. Alternatively, we can look at the reduction in area or the cross-section area of the material, in which case we switch A0 and the initial area and the final area to get a positive number, as the final area will be smaller than the initial area. We divide the change in area by the original area to give us the percentage reduction in area. If we look at the stress-strain graph, we notice that if we multiply stress by, sorry, that was strain. If we multiply stress by a little bit of by the strain, what do we get here? We are multiplying a force divided by an area by a change in length over the original length. So this is going to equal F times change in length divided by the original length times area. If you remember from in mechanics, a force times a distance, the distance, is equal to energy. The energy and the length times the area of the specimen is the volume. So this is telling us that if we integrate or find the area underneath the stress-strain graph, what we're calculating is the energy stored per unit volume as we stretch this material. And the resilience is the energy per unit volume the material can absorb without experiencing permanent deformation. It is equal to the area under the elastic portion of the stress-strain curve. Resilience is important for designing machines, for instance, or machine components that will experience impact, for instance. And we want to make sure that they can absorb the impact without deforming. So that's resilience. Toughness is related to resilience, and toughness is the energy per unit volume the material can absorb up to the point of failure. It's equal to the area under the stress-strain graph up to rupture. Which of these would you say is a tougher material? To the eye, it seems clear that the green area is larger than the area under curve B, part of which is shaded a peach color. So we know that the material B is going to be tougher than material A because it can absorb more energy before it ruptures. Toughness is measured using standardized tests where a pendulum mass is allowed to impact with the specimen. It actually starts off here. It impacts with the specimen which has been notched in order to provide a systematic systematic cracking. So as the material goes through, it cracks. The pendulum will not rise as high after the crack because some of its energy has been absorbed by the material. If the pendulum rises to the same height, that means very little energy was absorbed, which indicates a material that is not very tough. If the pendulum does not rise very much after impact, that means the material has absorbed a lot of energy during the impact, and hence is tough. The difference between the Sharpie and the ISOD measurements is the difference in geometry of the sample and the way in which it is held during the test. Please take a look at the video links I have put on that slide so you can see such a machine in action. Another material of interest is hardness testing. Hardness is the resistance to localized plastic deformation or resistance to penetration by a pointed penetrator or a pointed object. Typically what we do, we have a diamond indenter with a specified shape that is pressed into the material with a specified force. We then look at the indent that has been formed. The size of the indent gives us a measure of the hardness of the material. The larger the indent, the less the hardness. The smaller the indent, the harder the material. Here we see a hardness machine. The sample goes right here, and there's a sequence of operations to preload it before applying the force and measuring the amount of deformation that occurs. And this particular machine shown is fully electronic, but manual versions are also available. And a readout is given. Hardness units depend upon the type of penetrator, so it could be a ball, a large ball, or it could be a diamond braille. And we get different hardness tests for that. So the Rockwell, we get the Rockwell C. Okay, so we've got the Brinell test and then the Rockwell tests. So the Rockwell C is done with the diamond braille, and you can see it goes from 0 to 80. 80 being nitrided steels. So the Rockwell C is very good for looking at steels, for instance. But for softer materials, you may want to use Rockwell B or a Brinell hardness scale, which covers a wider range. There's also Knoop hardness and Moore's hardness, which is used in the study of rocks. So by drawing a line on this, we can convert between different hardness scales. So if I draw a line here and move it, here, so we can see that this is 30, 35. A Rockwell C of 35 is equivalent to roughly 110 Rockwell B. So if you see a hardness measurement, you will see the standard that was used to measure that hardness listed together with it to give it its full meaning. When materials are actually used, we have to account for variability in the material itself, as well as the unknowns associated with the loading conditions. Safety factors are used to account for the unknowns. Sometimes in the textbooks it is explained that a safety factor is actually an ignorance factor, to account for the fact that there are some unknowns associated with their application. For instance, with wood is a natural material, and there is wide variability between the strengths of pieces of wood, even from the same tree. Although wood is tested, it is prudent to apply a safety factor such that when we design a structure, we make sure that the stresses are a certain factor below what we consider the maximum allowable, or could be the yield stress or the rupture stress, the tensile strength of the material. For different disciplines in engineering, a safety factor will be applied. So for aeronautical engineering, certain components will have different safety factors. In building designs, a typical safety factor may range 3 to 4 for a residential building construction, but for critical buildings such as a nuclear power station, we may have to build those 10 times stronger than what we expect the maximum load to be in order to ensure safety and reduce the probability of failure due to unforeseen circumstances. There are two ways in which to do this. Let n be the safety factor. We can multiply the calculated stress. So this is the stress that we expect to be generated in material. When we multiply that by the safety factor, we will get the design stress. We need to ensure that our material will not yield or fail when stressed to that design stress. Another way is to divide the yield stress of the material by the safety factor being applied. This gives us a reduced value for the stress that is allowable in the structure.